All right, so this talk is going to be covering mobile application wrapping. This is relevant for BYOD, mobile application management deployment, solutions. We kind of ran into this while we were doing some of our own testing for clients, and then we did some of our own research on it. So really, it's a pretty cool technology. It's new. Not a lot of research out there for it, so we just thought it would be a cool thing to look at. So some high-level things that we're going to cover. We're going to do a quick overview of BYOD risks and threat scenarios. And the reason we're going to do this is just to get an idea of what are some of the main risks when you're doing a BYOD. I'm going to assume everyone here knows bring your own device already, so I'm not going to go into details with that, but more of what are the risks that an organization who's doing one of these deployments should consider. Just so we can stack that up, all right, we have these solutions, different vendors, different types of solutions. How well do these actually protect against those risks? Then we do a quick comparison of, there's typically two approaches to BYOD. There's MDM and MAM. MDM, there's mobile device management, and then there's MAM, mobile application management. We'll compare and contrast on why does MAM exist? What are some of the use cases for it? Then we'll start getting into some of the more technical stuff, and we'll talk about some test cases that we did during our research, and then dive into some common vulnerability patterns that we found with different solutions out there. And lastly, we'll do some sort of conclusion, talk about a testing checklist that we can all use to help make these products more secure in the long run. So a little bit more about the research. It's the currently there's it's being used more and more by organizations, and it's really cutting edge, and I haven't seen any research out there for it. So just something that we think that this should be looked at. And the interesting thing is, why isn't there a lot of research on it? If you think about it, a lot of these commercial solutions are really hard to get your hands on. Either you assess these things for clients who are really interested in getting these things tested to see if they're secure or not, or you have to somehow get it through a demo. And going through these demo processes, it's pretty annoying. I know when I did got access to one, you kind of got to go through live demos with these guys, and then you start getting invoice emails every other day, hey, are you guys ready to buy? And I'm no, not yet. Can I get another extension for another week? And but then you have to pretend you're interested in the product, or else you'll never get your hands on it. So doing the research is hard. So I have a feeling that's probably why there's not a lot of existing research for these types of solutions. It builds on, so last year at AppSec USA, I did some initial research on secure containers, just talking about some ways how they're implemented and some common security bugs we saw. So now we're going to see this later on that and these app wrapping solutions, at the end of the day, they are secure containers. The goal is to protect the data. They're storing these things in secure containers. So a lot of that stuff applied for these, but now we get to see it out in the real world and how it worked in commercial solutions. So we just wanted to share some of the common vulnerability patterns and kind of, how can we make these solutions stronger? And it's key thing about this presentation is we're going to be vendor agnostic. So I'm not going to be dropping names of any of the vendors we looked at, multiple reasons. We don't want to show preference for one vendor over another, and I also don't want to have to avoid cease and desist letters while I'm on stage because I'm talking badly about a vendor. So I just like that picture. I just want to hold hands and be friends with everyone. But at the same time, talk about what are some of the common vulnerabilities that we did find, so that we can make these solutions stronger. So let's dive into some of the major BYOD risks. Obviously, if you're doing BYOD, their employees are going to be using their own personal device, and they're going to be loading organization data on them. So a lot of sensitive data. There's emails, contacts, your address book, your calendars, probably even like client certificates to authenticate to some VPN and access internal apps, enterprise applications storing sensitive documents or other type of data. So, this one's pretty obvious, right? Lost or stolen device. If I'm able to steal your device and gain access to that data, that's bad. There should be some controls in place to prevent that from happening. Stolen device backup data. That data that's stored on the organization data is not always going to be on your device. Nowadays, backups are stored in the cloud. They can be stored on your workstations when you're doing backups. So, while you're on your workstation, personal workstation at home, that's probably not the most secure system out there. And there's a good chance you're like downloading, Frozen from BitTorrent off some Chinese dude, and these systems are not made to be like secure. It's their personal device. So having sensitive data on it could be an issue. Disgruntled former employees. You have an employee, works for your company. One day he's gone the next day. He might be angry, got fired, or just left. There should be some security controls in place for an organization to say, all right, he's no longer working for us. Even though he had data on his device, there should be a way for me to wipe it, for example, and prevent that device from accessing our networks. Malware, malicious apps, it's your personal device. If I'm sideloading apps on my device or downloading stuff from the App Store, there should be no way for those applications to gain access to organization data. Unattended devices, you leave your phone there for a second, I decide to pick it up. There should be controls in place that allow me to not be able to just open up the mail app or do whatever on your device without actually having, there should be things around to prevent that from happening. Bypassing client restrictions. So there's going to be some forms of client restrictions. Like maybe you don't want people running it on a jailbroken device, or maybe you don't want your employees doing like copy paste and putting it into some other thing, or maybe you want the organization data to only be available in a certain app and not be used outside of it. Malicious users on a network. You're at Starbucks doing whatever you do on your phone. There should be controls in place that ensures that the data is protected over the network. And then, obviously, with all BYOD deployments, since it is your mobile device talking to a server, there are going to be some internet-facing endpoints. Those should be protected. Out of scope for our research, we're mostly worried about focusing our research on just the client side of things. So we kind of eliminated anything that's server-based from this research. So the goal for BYOD is essentially protect the data, and it's easy to say, well, maybe you shouldn't be storing the data on the device, but in the real world, that's not feasible. You need to store the data. I need to have access to my email while I'm underground or not online, and just for performance reasons, caching is around. That data needs to persist on my device. It's something that has to be done. And then there's the two approaches, the MDM and MAM. And the MDM the goal is to protect, to kind of manage the device, but at the OS, the device level. So if I'm going to be setting policies, it's going to be at the device level. So if this is your personal device, if I'm going to set a passcode policy for 8 characters and timeout for 3 minutes or something like that, this is going to affect your whole experience of using that device. Where MAM, the goal is to be at the app level. So you can keep using your mobile device the way you always used it. If you don't want to have a passcode on your device, so be it. Since everything's being enforced at the app level, you can enforce the policies there. And there's a lot of BYOD vendors. So just so you have an idea of what are some of the big names you might actually recognize some of them. And this shows, like, this is based off of the Magic Quadrant and Enterprise Mobility Management Suites by Gartner. And apparently this is like the de facto thing that everyone like quotes in their white papers and like their their main sites saying, hey, we're a market leader in BYOD or whatever. So essentially it's like a quadrant, and anyone who's in the top right, those are considered the top players by Gartner. So for MDM, how does, since it's all done at the device level, very high level overview, I'm not going to spend a lot of time on it. Device does some enrollment to an MDM server. From there, the MDM server can push device level policies, can do push security commands to the device, so those get invoked immediately. Query information from the device, install, there's a bunch of other stuff that it can do. And a lot of this stuff is really dependent on the OS as well and what it supports. There's a lot of existing research in MDM. I think David, who's right here, did some stuff a couple of years ago on MDM, especially for iOS. And then earlier, yesterday, there was another presentation on mobile device mismanagement, which talked about a lot of the MDM stuff. The main drawbacks with MDM, which a couple of them I covered. So there's the strict policies. You're kind of hindering your personal experience when you're using these MDM if your organization is doing strict policies, right? The implementation is OS dependent. So depending on how the operating system, what APIs it exposes, that's what the MDM server can actually enforce. So, if it has something to install apps or remove apps or protect data in certain apps, it all depends on what it actually supports. And then there's some privacy concerns, Like, I'm giving this company now the ability to wipe my entire device at will. If I left the company, how do I know if, what if they decide to wipe my device and I didn't want them to do that? That's something I wouldn't want them to do. And also they can query a lot of information from your device, like the installed apps. If I have the new Kim Kardashian game installed on my device, I want to actually use it in my own privacy. I don't want the sysadmin to know that I'm actually running it. And data protection, so like the encryption, it's really hard to enforce how effective that encryption is going to be. So let's use iOS for an example. What an organization can do is they can set passcode policy, enforce passcode. And that'll turn on data protection, and data protection can be used by apps on a device. However, data protection is kind of like an opt-in, especially before iOS 7. If a developer didn't use the right APIs and set the proper attributes, that data would still be stored unencrypted. As of iOS 7, it now has a little more strict option, but it's not the most strong one. Like right now, I think the default is that it'll encrypt it with a key that's available once you enter your passcode once on your device. Then it'll be persist in memory until then. Where the more secure option is the one that persists a key, but then when you go into a locked state, it'll remove it from memory. So you kind of, you're not getting that full encryption. It's a little unsure. If I'm running an old iPad, because I don't want to buy a new one for some reason, that's going to be running iOS 5 because I can't upgrade anymore. You can't really protect the data at that point. So where does MAM come in? So MAM, as I mentioned earlier, is protection at the app layer, but it requires development of secure containers, which could be a little tricky, right? And complex. And it leverages this technology called let's call it application wrapping, where you have these existing applications, and I want to add security to these existing mobile apps. And that's what app wrapping is. So here's a really high-level overview. So you have an organization might have their own custom mail application, their own custom calendar application, and then these are going to be the apps that you're going to be accessing your org data from. And then you might actually have enterprise apps. Your company might have their own custom apps that they developed in-house that they want to deploy as well. They all get wrapped Suddenly you come out and now you can enforce policy, like you can enforce authentication, you can enforce data encryption, so on and so forth. So just like that app icon got injected with something, these apps are getting injected with some security. So high-level overview with some pictures, because it's always clearer with pictures. So you have an existing mobile app. The solutions typically will supply you with some form of a wrapping utility. And then this wrapping utility will inject some wrapping code, and we'll go over in detail on what are some approaches to injecting into an existing application. So this is causing some modification of the executables. And then it'll have to re-sign the application, and this re-signing is going to be with an enterprise certificate. And why do we have to re-sign it? Obviously, you just changed the executable. It won't run on a mobile device unless you re-sign it again. So now you have this brand new re-signed wrapped application. You're going to upload it to some MAM management server. Then the employees have their mobile device. They go to the app store of their choice, download agents, a MAM agent. This is what I'm going to refer to it as throughout the presentation. Log in, usually with their Active Directory credentials or whatnot, to this MAM management server. They might get, you'll likely see a store of what are some of the available apps that I can install, or maybe they'll just get pushed down once you use the app. But now from here, this is how the wrapped apps actually get pushed to your device. And then all of these wrapped apps will then contain secure containers. So let's walk through an example of iOS app wrapping. So this is with one of the solutions, and I'm not going to say this is how it works for every solution. This is just one test case. So we'll walk through how the process that we did, and you can probably apply it to whichever one if you ever get around to it. So what's the first step when you're trying to determine what changed, right? With, let's say something got patched. You obviously do get something, the pre-patched executable and the post-patched executable, diff them, and you know where to start looking, right? So I did the same thing. I got a pre-wrapped IPA file, and then a post-wrapped IPA file. And then unzipped it, compared the executable, and then diffed them. Opened it up in a hex differ tool, pointed out in red, where there was a change. Executables in iOS, they're Mako executables. So I open it up in a nice Mako GUI, go to the offset of where the changes were, and then that's going to point you in the right direction of, all right, this is where something changed. They modified this portion of the binary. So what was changed? They added in a new lcload dylib command to it. So this is just adding in a brand new dynamic library to the Mako executable. So now every time you run that application, you have code injection immediately. You are able to start running code. And then they also added in the dynamic library, which is going to contain all of the code that they want to execute. So we talked, how are they actually adding the security, right? This dynamic library, with Objective-C at least, you have the ability to do something called method swizzling, which is you can take an existing implementation and kind of swap it for your own implementation. So let's say you have application did begin launching or whatever that runs whenever iOS app starts, right? And I want to say, I don't want to run this right away. I want to run my own version where I can actually stop execution and enforce authentication. I can do that now. And then once you authenticate, I'll just call the original function again. So that's how they achieve code execution. And this kind of goes into play with how are they adding crypto, right? If you think about it, now you can do swizzling for pretty much any API, right? So let's say you have a NS file handler and you're writing data to a file. You can also swizzle that method and say, all right, don't just write to the file, encrypt it before you write to the file. And when you're going to read it, don't just read it, decrypt it first, and then read it. So this is how you're adding kind of that logic to it. And last but not least, well, actually not last, but the other thing in the executable that changed was the code signature, which is what we expected, or else it would never actually run. And then if we look at the info.plist file for the application, and this is like the main config file for iOS apps, you can see that they defined the brand new URL scheme. So this creates kind of like a new entry point to your application that you probably didn't know it was there before, but now it is, surprise. But this is like the main way that the MAM agent, the one that just installed you onto the device, and the MAM agent should be like considered like the brains of the operation. This is what's communicating with the server and like retrieving like commands like, oh, is there an updated policy, or is there lock initiated, or is there like a wipe initiated? Like it's listening, like it's pulling for these commands. So it needs a way to transmit those commands over to these wrapped apps. So this entry point that it adds is the main thing to it, how the MAM agent would actually start communication to those apps. How about Android? Android, if we crack open the post wrapped APK file, you can easily see that they've added some new NDK libraries. So this is like native code. And then if you crack open, you have the dex bytecode. You do like dex to jar, and then you can decompile the jar code, and then get some readable Java code. And this is how, step one of how to determine what changed. All right, I can look at the code and see what changed. So I opened up the main activity for this sample app that we wrote. It's just a test app, doesn't really do much, but I just wanted to see how does it achieve code execution. So I go look at it, and it's like main activity extends activity, which is what I had, right? But then if you actually scroll up over to the import statements, it's not calling the Android activity anymore. It's now calling their version of an activity, which they just added on to the code. And then if you look throughout the code just consisted of a bunch of the different ways you can write data, right? And make requests and all that stuff, just so I can test to see what was actually being wrapped. And a good chunk of like the common APIs, they're all just swapped. This is pretty much implying that the dex bytecode was actually modified, like from whatever I had as my let's see what example. Like a file writes, or the clipboard manager, or my web view. I didn't write that. That was totally changed at the bytecode level, and it's now calling their version of all that code. So a simple way to actually do this, there's like a library out there called ASM Dex library, and this allows you to actually modify Dex bytecode as needed. So how about entry points? You open up the manifest file, and then there's a large amount of additions to for entry points, and especially in Android, since there's so many ways to do IPC. There's like content providers, activities, services, broadcast receivers, and they pretty much added a little bit of everything up in there. So another high-level overview, right? Just so you get the big picture here. In the MAM world, you're going to have your native apps, your native mail app, your calendar app. That's for your personal use. Great. But then for all the enterprise data or your organization data, you're going to have the MAM agent, and then you're going to have wrapped managed apps. So a custom, like a mail app, a wrapped document viewer app, a wrapped address book, or whatnot, right? And these are going to be secured. These can enforce actual policies. Those can enforce data protection. However, what you don't want is any scenario where I can go from one of those wrapped apps out into a native app, because now I can't control that data anymore. So let's do a comparison right here. Why would someone use MAM over MDM? Well, the plus is you get a little more, personal experience is little better because you don't need to enforce strict policy at the device level. If I want to use Twitter whenever with like a 4-digit passcode and have access to it at all times and not have to unlock and enter my passcode all the time, I can do that. But if I want to access organization data, I'm probably going to have some strict policies just to access those apps. Less privacy issues. You can't query anything that you're not, as much as MDM does, because now you're kind of restricted to the sandbox and what it allows you to do. And you can enforce security better because this is all custom stuff. If I want to enforce my cryptography and my security, I can do that because we can actually write it. However, it's like a double-edged sword, right? Now you're dealing with custom crypto implementations, which everyone knows no one does right. Custom IPC implementations, because there's a lot of IPC occurring between that MAM agent and the wrapped applications. And there's also like the application experience. You're used to using your native apps. Now you have to use like these wrapped apps that might not be as good. So there's that. And then there's also like these security commands. From our experiences, they don't have the ability to. They could probably pull it off to do like a push notification kind of thing, but it's rarely ever seen. So a lot of times you have to deal with some of the OS level restrictions and have an application running and then pull to a server to see if there's a new command. And when you're dealing with like device wipes and all that stuff, you kind of want those to trigger immediately. So let's talk about like some of the security checks we're going to be doing. We're going to look at some of the like container authentication, the cryptography, the completeness of the secure container. So when I say completeness, what that means is, you're doing app wrapping. You've got your cryptography, great, but like how effective is that cryptography at encrypting everything that needs to be encrypted? Like maybe if I use one API, it encrypts, but if I use this other API, which they forgot about, then it won't be encrypted. So like testing how effective that is. The IPC, how that's implemented to ensure that another app can get access to it. The effectiveness of the security commands, so if I issue wipes, how effective would that be? And then policy configuration features, like what policies does the server actually have available to us to actually protect us from like some of the BYOD risks. We're actually going to skip over the policy configuration stuff. We'll include that in the white paper because there's a lot of cool stuff to cover that's kind of boring. All right, so let's go into some actual bug stuff. So when I think of like a secure container, I like to think of it like there's like 3 principles where if you break one of these, you'll probably have a broken solution. So all data stored by the app should be encrypted seamlessly. The strength of the crypto should never rely on any device level policy. And crypto keys must only be retrievable after or derived after you've fully authenticated. So let's dive into a vulnerability pattern here. So we're doing some reversing of a solution, right? We're going through the logic of the authentication, and then we determined that the actual like passcode that you entered on the device wasn't used to actually derive the encryption key protecting the data. So what that means is that all the key material stored on the device was stored, like all the key material used to protect the data was stored on the device as well. So the offline like authentication logic, if I'm trying to get access to a document offline, that was all like client-side logic. And as you can imagine, that can always be bypassed. And it violates principles 2 and 3 and kind of makes this solution provides you no real protection at all. It's just obfuscation at that point. You're storing something encrypted, but you're storing the keys like right next to it. So it's makes no sense. So let's walk through how this could be actually exploited, right? There's multiple ways to go about this. I could go and try to reverse the key derivation logic, go, oh, did you get the data from here, that data, put them together, hash them, and then you suddenly got a key, and then you decrypted it. There's a lot of work to try to figure all that out. So we took a little shortcut here. So we wrote a test app, just writes this line. This is just some plain text data. And then wrote it using the write to file iOS method, which is just common. And I'm expecting this to be wrapped and stored encrypted on the device. So it's wrapped, install the device, run the app, SSH in to my iPad, cat it out to make sure it's actually stored encrypted. I see gobbledygook. I'm like, all right, looks legit. Next. So then the approach we took for this is, if I'm able to inject into the running process, I can start actually kind of maybe leveraging that wrapping code. So I can just inject into it and read that file. And then I'm assuming that once I try to read that file, my read will actually be wrapped as well. And it'll just decrypt the file for me without me having to do any reverse engineering whatsoever. So I use Cycrypt for this for iOS. Sure, if you want to learn more about it, you can look at the 20,000 presentations that talk about it. It's really simple. It's like a weird mixture of JavaScript and Objective-C. So I just wrote a simple script that just tries to read that file using the NS file handler object, and hopefully that gets wrapped, right? And to add a little kicker to this, even if you were to trigger enter the app in a locked state, so I'm currently not authenticated to the app, I need to authenticate, I can still the process is still running, right? So I can just get the process ID for the process, and then use Cycrypt, run my script, and then I can retrieve back a plain text version of that data without doing any reversing whatsoever. Well, other than finding the bug to begin with. Another common pattern for authentication is the decoupling of the passcode verification and the key derivation. So what that means is, you might have an offline passcode prompt and then to access your data, right? You might be deriving the actual encryption key properly. You're doing PBKDF2 with 20,000 iterations with secure salt, doing the whole bag of tricks, right? But there might be some logic before that key derivation where it's actually, doing some sort of a checksum, it's trying to validate whether that passcode is correct before it starts deriving a key. So this is a common bug that we found where the key derivation could be strong, but then you have this really weak passcode verification that I can now use that logic to actually brute force instead of brute forcing the key derivation. So we found one bug where they were doing an unsalted SHA-256 as that passcode verification, which is pretty terrible considering not all solutions do this, but sometimes enterprises actually use their Active Directory credentials as the passcode to their MAM devices because they have those accounts, they have those passcodes already, they're maintained already, and it's just so they don't have to memorize multiple passcodes. So if I'm able to steal your device and do this really quick offline brute force, because it's unsalted SHA-256, and get access to your Active Directory, that's pretty terrible. So here's just some output. We found this seed hash in a config file, and then using some straight up Python, you're able to just verify whether my passcode matches it, and it does. Let's get into some crypto stuff. So crypto is really hard. And there's so many ways to do it wrong, and it all depends, what algorithms you're using, what modes you're using. There's just different types of attacks for different types of crypto, and it's, I'm not going to cover it right now because you can have I'll take a whole class for a whole semester just covering these things. But I'm going to discuss why these are going to be common, right? So what we've found is that the de facto library to use in these solutions is typically OpenSSL. So you're always going to see like this OpenSSL native library injected, right? And why do they use OpenSSL? Because it's FIPS compliant, and you can say, all right, check, 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 I'm FIPS compliant, right? Add it to my white paper, I'm good to go. But the problem is that with OpenSSL, it's not really a high-level library, like maybe if you're familiar with like Keyzar or something like that, where it tries to eliminate some of the difficulties of crypto from like developers. It tries to do things as right as it can or knows how to. With OpenSSL, you're working with pretty low-level stuff right now, and there's a high potential of having implementation flaws when you're doing that. What I will talk about is one interesting kind of bug that we've found in the solutions, but that I really haven't really seen other people talk about, so I guess I'll talk about it. So let's think of this scenario, right? You have this master key, right? I'm telling you, don't store it as a string object. But you're commonly going to see this, though, because I've seen solutions that leverage SQL Cipher to do some of their SQLite encryption. And the problem with SQL Cipher is that if you look at the function there, the second parameter, that's going to be the passcode that's going to use to actually protect that derive an encryption key and protect that data, right? So now you're passing in some secret as a string, and there's a high potential that they're probably going to reuse the same master key that's used to protect all the data as that value. So what's the risks here, right? Storing as a string, there's a good chance it might be stored in the heap, and then if it's on the heap, there's a good chance that it'll persist for a pretty long time due to garbage collection not happening very quickly. And for my own testing, I've done this for 15 minutes or so, and it still persists in memory. But another cool bug, which I'll talk about, is more of this character encoding, a subtle bug that can kill the entropy. So here's some code that we got from an obfuscated solution. The cool thing about sure, you can obfuscate a lot of the custom code, but then you're never going to be able to obfuscate kind of PBKD, the PBE key spec library, because that's kind of built into Android. So that kind of if you're trying to figure out how to hit these sweet spots, there's a good chance they're probably going to be using this to derive an encryption key. So you can just search for these in the code and be all right, this is where the magic's happening. All right, so we look at it and we're oh, okay, they got 20,000 iterations. They're taking in the first two parameters, and they're going to be using that as assault and something else. And they're creating a 256-bit key. That's going to then be assigned to an array of byte variable, and then array of bytes, and then the return value is just passing it into a string. Okay. So let's look at one of the approaches that I take when I'm dealing with obfuscated code and trying to reverse these solutions is I use mobile substrate, which I'm not going to go into details because it'll take 20 minutes. But if you look at my old presentation, I talk about it more. But approaches I take is I find interesting functions, I hook them, print out the parameters. If it's obfuscated, there's a cool trick that lets you that I use to just. It's kind of if you use GDB, you can do a BT, but it kind of I just throw a stack trace and just print it out just so I can get a call flow of the application. Be all right, I just hooked this, but now I know exactly what call that and then what call that, and I can get an idea of what's the flow without having to go crazy on the obfuscated code, searching all right, what called f.e.z, and then that got called by a.g. by it's a lot less confusing. So first, I print out the parameters. It takes in my passcode. It takes in some really long value. It's probably assault. Then I have my call flow that I can use to do additional reversing. And then at the bottom, you'll see that in red text is the return value. So let's look at what the return value is. And what's interesting about this is that what the hell are these EFBFBDs that are all up in my master key now? And the problem is that if we go back and look at what the return value is, it took the derived key, and that's going to contain the full byte range of that's possible, and then it's going to be set to the string value, right? And the interesting thing is that for Android, and this applies to pretty much anything, but for Android, it's going to the default char set is UTF-8. So a lot of the byte values that are coming out are not going to be supported by UTF-8. So what it does is it's like, oh, I don't support this character. I'm just going to assign this new one, replacement char, and that's EFBFBD. So essentially what's happening here is that you're killing the entropy of that master string, master key. In this case, it went from like 32 bytes to 22 bytes. But if you think about it, it all depends on what the output of PBKDF2 is going to be, and that could range from pretty much anything. It's like random, right? And if you're dealing with like, this one's like 256-bit, but if you're dealing with like 128-bit keys, and you start killing a lot of this entropy, now it's getting to scenarios where some of these issues can potentially be susceptible to like attacks. Incomplete secure containers. So everything that is supposed to be encrypted should be encrypted. So what was our approach to finding these types of issues? We developed a test harness. We cracked open documentation, looked at all the APIs, and we're like, all right, this probably writes some data, this writes data, that might cache data, that caches data. And we just wrote test harness applications and then got them wrapped. And then we see what got stored in plain text, what didn't. So let's walk through some of the common APIs that we saw that were missed. So for iOS, we saw that keychain stuff typically weren't wrapped. Why it wasn't wrapped, I'm not sure. Maybe they think that keychain is secure already, but if you're not relying on device level policies, the keychain, if you can't enforce passcode on the device level, the keychain is not very secure. And that's user defaults, which I'm kind of surprised, but it's pretty bad because 4 out of 10 pen tests, I see that that's like a go-to place for people to store their credentials apparently, but so them not protecting NS user defaults would be an issue. iCloud APIs. Interesting about iCloud APIs, you're writing data directly to the iCloud, but it stores a cached version of it on the device as well. Maybe they didn't take that into consideration, so they just didn't encrypt it. With Objective-C, you can write inline C or C++, and then, so if I was to write an app and then decide I don't want to use Objective-C, I'm cool, I'm going to use fwrite and write my data that way, then that data would be stored unencrypted even though it was wrapped. Web views, you got HTML5, you got a SQLite data, local storage, all that stuff. This might be common to see that they didn't take those into consideration. Persistent HTTP cookies, you're creating an SURL request, and then suddenly a persistent cookie gets set by your main organization's SSO service. That persistent cookie, which is like the keys to the kingdom, could be stored in plain text. Document caching. So when I say document cache, I'm talking about, you probably use iOS, right? You open up a file, it gives you an option to open in. You can pick which app you want to use it. The moment you pick another app, a copy of that file gets made to that other app just to bypass kind of like the sandbox restrictions. So a copy gets made behind the scenes. We found that that copied file never gets encrypted and stored properly. So there's another thing to look at. And file names. We'll talk about a cool thing about file names and why that could potentially be an issue. But like one thing off the top of my head is, one of the most common apps are going to be like a mail app, for example, right? And what mail apps have file attachments, and it's a good chance those file attachments will likely contain sensitive data. How about Android? Some stuff we saw were like file system NDK was never wrapped. An interesting bug that we ran into was like symbolic links. So like this one was pretty interesting where they had some logic where depending on the symbolic link it'll decide to encrypt it or not. And then they forgot like /SD card. So that's like the worst possible place on an Android device you could store data because there's no file system permissions and it's like external media. And the worst thing is that since they're not encrypting it, they have no idea that it was actually stored there. So if you were to do like a remote wipe, that data would still stay on that SD card and never get wiped. Web views, any sort of like reflection where you can run commands like do runtime exec to write to a file or do like Java reflection, those wouldn't be protected. And file names as well. How about IPC? So IPC relies, like this solution relies heavily on IPC, and I talked about that earlier, right? What type of data is being passed between the IPC? There's going to be policies, so updates to policies saying, all right, this specific app here should have timeout of 5 minutes, and then data jailbreak detection, and forbid open-ins from there, or forbid copy-paste. You can enforce a lot of stuff. And this is all managed at the app level, so each app can have different sets of policies. So there needs to be a way for the MAM agent to communicate that stuff, and this is how it does it. Commands, if it needs to wipe from like the MAM agent and wipe another app, it's going to be passed through this IPC as well. Crypto keys could be potentially passed through here, and maybe even offline authentication data. So maybe an app needs to actually do offline authentication. So that data, the data required to pull that off, like to do a PBKDF2 and then compare it with something, that data would be passed in. So what are some considerations for IPC? There's keychain access groups, right? The problem with keychain access groups is the MAM agent is going to be signed by the vendor. You download it from the App Store. That's going to contain a signature from the vendor. The wrapped applications are going to contain signatures from your enterprise. So totally different developers. You can't even leverage access groups for this. URL schemes provides a way to call into another app, but that's a terrible user experience. If you're using an app and it suddenly starts flipping between applications, that's going to provide a pretty bad user experience. But it does provide the ability to do some form of authorization controls based on the bundle ID. And there's data size limitations since it's just a query string. So the common way to do IPC on these solutions is the UI pasteboard. And why do they use UI pasteboard? Because it allows large data and it has a better user experience. This can all be done in the background, just polling for it to see retrieving data and modifying that data. The problem is with the UI pasteboard is that if you know the key or the name to access that pasteboard, any app on the device can access it as well. So the main security considerations are it can be read or modified by anyone. So it should be encrypted. But then you start thinking, how do I protect the key? How do I get this key that I'm doing this crypto from one app to another? So that's something that you need to audit on your own and figure out how that key exchange is actually happening. Common way to pull this off is using URL schemes, but that's tricky on itself. They have to do the authorization right, and they have to, in order to avoid like malicious apps, you have to keep track of what apps you've installed, which ones you've uninstalled, just so you know it's not an app that you're not expecting. For Android, you have intents, but the same type of issues apply here, where it's all the permissions for Android are all signature-based, but you're signed by two different app developers, so you can't really leverage the built-in security controls for intents. So you're going to see a lot of programmatic checks within the applications, and apps can verify the app that just performed that call by doing like binder get calling UID using the package manager app, and then you get an application name. But then that application name could, of course, could be like a malicious app spoofing it. That's why a mobile agent needs to keep track of what apps is installed or uninstalled, since an app name, only one app with the same name can exist on a device. So here's an interesting attack dealing with the unencrypted file names, right? So we looked at an Android manifest, we found an activity that was exposed. Even though an application is like if you're not enforcing that authentication on every single activity, it can pretty much be brute force. So I can hit that activity and not actually authenticate. So using like ADB shell, no rooting required or anything like that, I can invoke activity and potentially bypass the whole login screen. So here's like an app. I'm currently unauthenticated. I'm like, all right, cool. If I just type that, plug it in, type the ADB command, I can then bypass it and access any unencrypted file data that was on there without having to actually do any work. So it's kind of interesting. Effectiveness of security commands. This might seem pretty obvious, but like the common thing we've seen with MAM solutions is that they need to be running so that they can poll. You need to ensure that all the application data is deleted. Even though that seems really obvious, it's not always the case. Wipes should apply to the agent and the wrapped apps. A lot of times we saw it apply to one, but not everything. And lastly, let's get into the conclusions. So initial research found, we uncovered some vulnerabilities. All the vulnerabilities we've found, we've disclosed to the vendors. They've all been responsive, and most of them have been fixed already. But the problem is that, and the security posture for these MAM solutions have gotten better over time. We've been doing this stuff for the past year, and they've dramatically gotten better. However, I've only looked at a small subset of them, so there's still more that can be done. So what I'm pretty much doing is like, from the testing that we've done, we've been developing like these checklists of what are some of the things we're actually testing for when we're looking at these solutions. So we developed like right now we're like over 50 different security checks. So hopefully everyone can like leverage these. If you're an organization and you're shopping around for these solutions, maybe you can use this checklist to, ask the right questions to the vendors. Like, are you guys doing this? Are you guys doing this? How are you guys doing that? You're equipped, you're smarter with these checks. You know what to ask for. If you're a vendor, now you have the ability to say, oh, cool, now I have a baseline. Actually, let's double check our solution, make sure we're actually like following these types of security practices and we're not vulnerable to these types of attacks. And for security testers, now we have like a baseline, or like now we know if you get put on an assessment to test one of these for like your client, now you have something to work with to actually get started with. So shout outs to my partner who couldn't make it, but he helped out a lot. GDS research team for giving me the time to work on this and for QAing my stuff. And then the white paper is going to be pretty long. Covers a lot of stuff that I didn't have time to cover here. And it's going to have this whole checklist thing in there. So we're still working on it, but it's going to be released. And don't worry, I'm actually going to release it. I hate when people say they're going to release something and don't do it. So pay attention to our Twitter and our blog, and it'll be announced sometime soon. Thank you.